Hey, let's talk about making solutions, the actual process. It's me, Moser, and after this video, you should be able to identify factors that increase the rate of dissolution, describe solution equilibrium, distinguish between saturated and unsaturated solutions, and describe the effect of polarity on solute-solvent interactions. Not so much, right? Okay, if you've made Kool-Aid, you know how to dissolve a solid in a liquid. And you know that though solutions can be in any phase, we very often talk about them as solutions made of a solid solute and a liquid solvent. So, you've got this vessel, you got some water, you throw in your Kool-Aid powder and your sugar. How do you get that stuff to dissolve, to become a heterogeneous mixture? I see three possible solutions. To increase the rate of dissolution, you could increase the surface area of the solute. In other words, break those chunks up. You know that if you've got a big lump of sugar, it won't dissolve as quickly as finely powdered sugar. So increasing the surface area of the solute increases the number of collisions that occur between the solvent and the solute, hence increasing the rate of dissolution. Well, what else could we do? We can agitate the mixture, in other words, stir it. Again, this just works to increase the number of collisions that occur between the solute and the solvent. That's not so hard. Well, what's our last option? Oh, heat the solvent. Heat it up. You know that when you're making Kool-Aid, warm water will dissolve sugar more quickly than ice-cold water will. Why? Well, the molecules of a hot solvent are moving faster than the molecules of a cold solvent. And the faster those molecules are moving, you got it, the more collisions we have. Therefore, these things would increase the rate of dissolution. Break it up, stir it up, heat it up. That's easy. When we talk about solutions, we often talk about unsaturated versus saturated solutions. So an unsaturated solution is one that can dissolve more solute. So if we stir it or heat it or break up the chunks, we can get more of the solute to dissolve into that solvent. But in a saturated solution, it's holding all the solute you can at that temperature. So even if you stir it, even if you break up the chunks, you're not going to get it to accept any more solute. Well, this really kind of gets to the question of what is the process of dissolving anyway? Dissolving is actually a balancing act between two opposing forces. The force of particles leaving the solid state and going into solution, this is called dissolution, and the force of particles leaving the dissolved state and re-entering the solid state. This is called recrystallization. When we hit a point where the rates of dissolution and recrystallization are equal, we've hit what we call solution equilibrium. This is the point where we've got a saturated solution, and at that temperature, we're not going to get any increased dissolution. Okay, that's all well and good, but can we figure out how much stuff we can get to dissolve? How much stuff we can get in when we're into a solvent when we know that we're going to approach the point of solution equilibrium? Yes, glad you asked. Solubility for any substance is the amount of that substance that can be dissolved by a specific solvent at a specific temperature. And nobody memorizes this stuff. You just look it up. Hey, check it out. It's a solubility table. So, this is the solubility of a set of solutes as a function of temperature. And notice that we've specified the solvent, and we've specified the amount of the solvent. So we specifically are talking about per 100 grams of water. There's one other thing that's specified, which is the temperature. So at 0 degrees, we could dissolve 122 grams of silver nitrate, but at 20 degrees Celsius, if our water is at 20 Celsius, we could dissolve a whopping 216 grams of silver nitrate. Ah, remember, when we heat it up, we can dissolve more stuff. So, to figure out if a solution is saturated or not, we use a solubility table like this. Let's look specifically at the line entry for potassium nitrate, KNO3. If we have 100 grams of water and 25 grams of potassium nitrate, and the solvent is at 20 degrees Celsius, do we have a saturated solution? Well, we would go in and look at the column for 20 degrees Celsius. We see that at 20 degrees Celsius, 100 grams of water should be able to dissolve 31.6 grams of potassium nitrate. What this means is that a solution containing 25 grams of potassium nitrate at 20 degrees Celsius is unsaturated. We could add more solute and get it to dissolve. Cool. I mean polar and polar. Huh? Well, funny, we've got a polar bear and a polar bear, but here we have a polar bear and a non-polar bear. Well, this is because in chemistry we talk about the idea that like dissolves like. The polar bears are just fun. Polar solutes are best dissolved by polar solvents. And a polar solute, or a solute that's got a region of charge on it, like an ionic solid. Non-polar solutes are best dissolved by non-polar solvents. Why won't oil and water mix? In other words, why won't water dissolve the oil? Because water is a polar molecule and oil is distinctly non-polar. They don't mix. We say that they're immiscible. On the other hand, water, polar molecule, and a water-based food dye, which is also a polar molecule, mix quite nicely. They are what is said to be miscible. Excellent. Okay, can you identify factors that increase the rate of dissolution? Describe solution equilibrium, distinguish between saturated and unsaturated solutions, and briefly describe the effect of polarity on solute-solvent interactions? Excellent. If not, ask questions.